Hello everyone, welcome to this neural network from scratch series lecture. Up till now, we have looked at forward pass and we have looked at the backward pass. We have had several lectures on both of these sections until now, and now we will begin to cover one of the last sections in this neural networks from scratch series, and that is regarding optimizers. So until now, we have learned that, let's say, if we have a neural network such as this, which has weights, which has biases, and which has a stack of neurons and layers, we know how to find the outputs, we know how to find the loss function in the forward pass, and we also know how to find the partial derivative of the loss with respect to the weights and biases of each and every layer of the neural network. We also know how to find the partial derivative of the loss with respect to inputs of each and every layer of the neural network. And we also know how to find the partial derivative of the loss with respect to the softmax activation function or the ReLU activation function. Great. So let me introduce the problem which we are trying to solve in the first place. The problem is that we have a data set such as this, and every data set has two attributes. So on the x axis, the attribute is x1, and on the y axis, the attribute is x2. And each data point can belong to either of the three classes. It can belong to the red class, it can belong to the green class, or it can belong to the blue class. Our goal is that we want to design a neural network and optimize the weights and the biases of this particular neural network, so that if I give you any new point, such as let's say this point which was not there in the training data, it should correctly classify it as red. If I give this particular point, the neural network should correctly classify it as green. That's the main purpose. And up till now, we have seen how to find the uh, loss in the forward pass and how to find all the gradients in the backward pass. But we have not seen how do you get to the optimum weights and how do you get to the optimum biases. So for example, if your loss function looks something like this, and you want to get here, which is the local minima, or rather you're looking at the global minima if the loss function is more complex, you want to get to this minimum point ideally. And if you start here, this is clearly not the lowest loss, right? So somehow you have to go from the starting position number 1 to the position number 2. Why we learn about optimizers is all about this journey from point number 1 to point number 2. Optimizers will help us to get to point number 2, or they will help us in this journey of going from point number 1 to point number 2. In one of our previous lectures, we have covered the importance of gradients in optimizers, right? If you start from this point, uh, it turns out that the best direction to move is the direction of the steepest descent. So ideally, we would want to move in this direction, right? So if the loss function is L, and if the parameters are W, it turns out that partial derivative or gradient of L with respect to W is the direction of steepest ascent. So it is this direction. So partial derivative or gradient gives the direction which we should move for the largest change in the function or largest change in the loss. So naturally, if we take negative of this, so negative of partial derivative of L with respect to W, or negative of the gradient, is the direction of the steepest descent. So negative of this gradient gives us the direction where we should move so that the loss function decreases the fastest. So this is the direction where we should be moving. And it's because of this intuition, that's why we spent so many lectures on back propagation and we spent so many lectures on calculating these derivatives, and now you will see how useful they are. Essentially, the main idea is that moving in the direction of steepest descent or moving in the direction of negative gradients is the best strategy which we can implement to minimize the loss function. So let's say you start out with random weights and you start out with random biases in every layer of the neural network. Obviously, that won't be the optimal loss, that won't be the lowest loss. and that's fine. So we will implement an iterative procedure where we will keep on updating the weights and biases. The simplest way to do this updation of the weights and biases is something called as gradient descent. And now there are many forms of this, but today we will look at the simplest version of updating weights and biases through gradient descent. We will also look at coding this in Python. So the simple idea behind gradient descent is that you start with random weights and biases and you perform iterations. In every iteration, what you do is that you move in the direction of the steepest descent. So for example, you update the weights by this formula. So weight new is the weight original minus alpha times the gradient of L with respect to W, and alpha is my learning rate. Today we will talk a lot about this learning rate parameter, because when we do gradient descent is the only parameter which we can vary. Remember that although I have written partial derivative of L with respect to W, this includes all the weights of this neural network. So for example, if you look at the first layer, every neuron has two weights. So there are six weights in the first layer. In the second layer, every neuron has three weights associated with it. So there are nine weights in the second layer. So totally, if you look at this neural network, there are 15 weights which we need to update in every single iteration. The larger the neural network is, the more weights we need to update. Similarly, we do this procedure for bias also. We start with random bias values, which is typically even 0, and then we subtract the learning rate multiplied by the gradient of L with respect to the biases. Similar to the weights, each layer and each neuron will have a separate bias. So for example, in the first layer, every neuron will have a bias associated with it. So that's three bias terms. And in the second layer, which is also the output layer, every neuron will have a bias associated with it. So that's again three biases. So there are total of six bias terms, and there are a total of 15 weight terms which need to be optimized for this particular neural network architecture which we have chosen. So this update rule which I have mentioned here, that needs to be applied for all the weights and for all the biases. And remember that when we need these partial derivatives, we have already found these during backpropagation. So when we instantiate a layer class in Python, we will have a forward method in that layer and we will have a backward method in that layer. What the backward method will do is that whenever the layer is called, it will automatically store the value of the partial derivative of the loss with respect to the weights, the biases, and the inputs of that layer. So all of these gradients or partial derivatives will be available to us when we do the forward and backward pass. I have spent a lot of lectures in this series on the backward pass, especially. So please have a look at it. That way, you'll appreciate this lecture much, much more. You will clearly understand why we spend so much time on back propagation. Because once you do all that hard work, now comes the easy part where you really, really can um use the knowledge which you have gained in the previous lectures. Okay, now that you all have this understanding, let me take you through the code file which we are going to implement. So today the main task for us is to implement the gradient descent optimizer in Jupyter Notebook. And the problem which we are considering is the same problem which I explained to you on the whiteboard. We have this data set and we are going to construct a neural network which basically takes in any input and classifies it into three categories: red, green, and blue. Remember that we have two activation functions here. The first layer will have the let me draw it in or write it in different color. The first layer will have the ReLU activation function, um, and since this is a classification problem, my final layer is going to have the softmax activation function. Okay, so this is the problem which we have. In the last lecture, we saw that how we defined classes in the forward pass and the backward pass. So we had a class called layer dense to create the layer. We had a class called activation ReLU, which defines the ReLU activation class after the first layer or the first set of neurons. Then we have the second layer, and then finally we have the combined softmax plus categorical cross entropy loss class at the end. Remember that since this is a classification task, the loss function which we'll be using is something called as categorical cross entropy loss. And I already have a lecture for this in this series if you are not aware of this loss. So these are the classes which we have. And now let us start looking at optimizers and gradient descent and how to implement this in Python. So we will define a separate class for the gradient descent. So this is not a stochastic gradient. So let me just change the name to GD, optimizer underscore GD. But for the sake of reference, let's just keep it like this. Okay. So now when you create an instance of this class, the optimizer SGD class, it will first call this init constructor, which will take learning rate as an argument. Remember, I mentioned that for gradient descent, the only thing which you can vary or control is the learning rate. So initially, when we get started, I'm going to set the learning rate to be equal to 1. So when we create an instance of this optimizer class, the learning rate will be set to 1. And then what we will be doing is that we'll call this update params function, which will take the particular layer as an argument. So whichever layer we are considering, we'll look at the weights and biases of that layer, and then we will update the weights and biases of that layer by subtracting the learning rate multiplied by the partial derivatives of the weights and the partial derivatives with respect to the biases. You might be wondering, where do these quantities come from? So these partial derivatives actually come from the backward method, which is defined in the layer dense class. So let me actually show you the layer dense class quickly for someone who is directly coming to this lecture. So if you look at the layer dense class, it has a forward method like this, and it has a backward method. What the backward method does is that it stores the gradients of the loss with respect to the weights, the biases, and the inputs of that particular layer. So the partial derivatives with respect to the weights and biases are what we are accessing over here when we update the weights and the biases of that particular layer. So the update params method is very important in this optimizer class. Okay. Now, since this optimizer class has been defined, we can just integrate it with the rest of the code. So first we have the data set, which has 100 samples and 3 classes. It's called as the spiral data set. The reason it's called spiral data set is because the data set itself looks like a spiral with 3 categories: red, green, and blue. Okay, then we will first create the initial layer. So here you can see that the initial layer has 2 inputs, and I'm going to use 64 neurons in the initial layer. So for the sake of representation here, I only showed 3 neurons, but for the code, I'm going to use 64 neurons. So I have 2 inputs and 64 neurons in the first layer. I'm going to chain it with an activation class, which is ReLU. Then I'm going to define the second layer, which will be having 64 inputs, which are here 64 inputs. And then finally, I'll have 3 outputs: R, G, and B. So it will have 64 inputs and it will have 3 neurons, uh, which are the output values. So remember that this layer dense class, the first argument is the inputs to those particular neurons, and the second argument is the number of outputs. So in the second layer, if you see, second layer will receive 64 inputs and we will have 3 outputs because we'll need to classify whether it's R, G, or B. And then finally, we will chain a combined class of softmax and categorical cross entropy. In the previous lectures, we have seen why we define this combined class. Ideally, you can even define a softmax separately and the loss separately. But then in backpropagation, it gives us a tremendous advantage if we define this combined class, because calculating the derivatives just becomes that much easier. And then finally, we create an instance of the optimizer HGD class, which we have already defined over here. Okay, now what we will be doing is that we will be performing iterations. So we will be performing 10,000 iterations of the forward pass and the backward pass. And after each iteration, we'll be updating the weights and the biases of every layer according to the update rule of gradient descent. So initially, let's do the forward pass. Dense one dot forward. What this will do is that it will take the first layer and then it will calculate the output from every each of the 64 neurons. That output will be just W transpose X plus bias, where X is input and W is the weights of the first layer. Then we will apply the ReLU activation. So activation one dot forward, dense one dot output, which means that we'll take the output coming from the first layer and then we'll apply the ReLU activation. Then we'll move to the second layer. Remember, the input to the second layer is going to be the output from the previous layer. And then the output of the second layer we are going to pass to the loss activation dot forward. What this loss activation is going to do is that it will calculate the softmax output predictions, plus it will also calculate the cross entropy loss. So it will be doing two things. And then we have a code which calculates the accuracy based on whether the prediction values match the correct inputs. What's very important to note is that we have a backward pass over here. So we'll start it from the last layer. So first we'll call loss activation dot backward. Remember that the backward class or the back propagation always starts from the last layer and then we keep moving right to the first layer. So first we will do the backward pass on the loss activation, which is the combined softmax plus categorical cross entropy loss. And then what we'll be doing is then we'll be back propagating through the second layer. We'll be back propagating through the ReLU activation, and then we'll be back propagating through the first layer. Remember, when I'm saying back propagating through the second layer and first layer, whenever I call these commands, we'll be storing the partial derivative of the loss with respect to the inputs, the weights, and biases of that layer. So in this code we are going to access the partial derivative of loss with respect to inputs, but when we come to the optimizer we'll be accessing the partial derivative of the loss with respect to the weights and the bias, because remember the update params function will require the partial derivative of the loss with respect to weights and bias of the particular layer. So then finally what we'll be doing is that for both the layers, we'll be calling the optimizer.update params. So for the first layer, we'll call this, which means that it will update the weights and biases of the first layer. And then we'll call this for the second layer as well. So it will update the weights and biases of the second layer. And as the iterations are proceeding, what we'll do is that for every 100 epochs, we'll be printing the accuracy and the loss. Remember that epoch is going through the entire forward pass and entire data set once. So when we are doing 100 epochs, we'll be going through the entire data set 100 times. Remember that the data set consists of 100 samples. So this is the simple code. And if you have understood the forward pass and the backward pass, the only thing which we have added here is optimizer.update params in both the layers. So now I'm going to run this piece of code and let us see the epochs and the accuracy in every epoch. So here you can see that the epochs have started and I'm going to run 10,000 epochs. The accuracy is 0.33 initially, which is pretty bad, right? It's like if we are going to determine R, G, and B and classify among three classes, 0.333 is just like a coin toss. It's just predicting one third probability we are correct of our predictions. But you can see that as the epochs are increasing, the accuracy is increasing. This indicates that we are kind of moving in the correct direction and the loss is also decreasing, which is good. This is the whole purpose of gradient descent. But as you can see, as the epochs kind of increase further and as we reach 6900, the loss has started to stagnate. And when we reach 10,000 epochs, we'll see that the loss is 0.681. So the loss really stagnated in the last 1000 to 2000 iterations. It did not decrease too much after this. That's the first observation. In fact, even if you run this for 1 million more iterations, the loss will not decrease too much further. So you might be thinking, what happened here? Is this the best we can do? Before that, let me actually show you an animation uh, with respect to what we just saw. And so this is the spiral data set which we are considering. And we took a learning rate of 1, right? So this animation will show you what is the answer after these many number of epochs. And that answer corresponds to what we just ran in code right now. So as you can see, the optimizer is running, and here you can see the different colors, and you can see the loss and the accuracy plotted on the right hand side. Ideally, if we have done a good job, what will happen is that the red, green, and the blue. So let me again pause here. Okay, now look at this image. We have almost reached the end of the simulation, but we are nowhere close to classifying the red dots into this red color, the blue dots into this blue color, and the green dots into the green color. Ideally, if our optimizer is correct, the green background should only correspond to the green dots, the red background should only correspond to the red dots, and the blue background should only correspond to the blue dots. But now look at this data point over here. It belongs to the blue category, right? But its background is red. So it's incorrectly classified. In fact, all the points here in the top right, they are blue, but they are in the red background, which means they are incorrectly classified. This means that we have clearly not done a good job with respect to classification of the data points, which was our initial task. Look at this data point, for example. It's a green data point, but it's being classified as blue. That's also not good. If you look at the plots on the right hand side, you will see that the accuracy stagnated to around zero point 0.6 or zero point 0.7, and the loss also stagnated to around zero point 0.8 or zero point 0.7, and the learning rate was fixed as well. So this clearly shows that the gradient descent, although it's good, we decreased our loss definitely. As you can see in this plot, we decreased our loss, which is good, but we have not reached the optimum value. So now you might be thinking that, okay, what is really happening here? So it turns out that what's happening is that you are probably getting stuck in something called as a local minima. So when we look at neural network, the when we look at neural network, the loss function landscape is not as simple as what we considered over here. The loss function landscape is in many dimensions, and it can be very complex, and it can look something like this. This is just for illustration purposes. So if you look at the loss function landscape over here, you can see that it has multiple local minima. What local minima means, that it's a point which is the lowest value but in a specific region. For example, if you look at this particular point here, which I have marked here, and let me actually mark it in a different color, just so that I show it in a better way. So if you look at this particular point, this is clearly the global minima. What global minima means is that if you look at the entire loss function, this is the point at which the loss function reaches its lowest value. So this is the global minima. But at several places before the global minima, you actually have local minima, which are localized regions where that point is the minima. So if you look at this point, and if you consider only this much area, this point is the lowest in that area. If you consider this point and only consider this much area, this point corresponds to the lowest loss in this area. Similarly, for this point and this area, that's why these 3 points are called as local minima. Okay. Now imagine that if you start from this particular point, let's say if you start from this point, and if you start with the gradient descent, and let's say if you go here, you go here, and you go here, and then you get stuck here, and then it really becomes difficult to come out of this local minima. That's why the loss function actually stagnates. That's why the loss function actually stagnates. So let me write this over here. And this is exactly what we observed, right? In the training process, the loss has clearly stagnated. So this might indicate that we have been stuck in a local minima. So the parameter which we vary, learning rate, is very important. It turns out that if you have a very high learning rate, that is also very bad, because then we'll just keep jumping around here and there, but at least we'll escape the local minima. But if we have very low learning rate, we might get stuck in a local minima. So let me show you some animations. Here is an animation of a learning rate which is too big. So let me start this from scratch. Okay, so as you can see, this is the function, and since the learning rate is very high, we just keep bouncing from one point to another, and it's very difficult to reach the global minima, which is over here. We are getting close to the global minima, as you can see, but it's a very long process, and we just keep oscillating back and forth. This is the problem with a very high learning rate. Now, if you want to look at low learning rate, there is another video which I want to show. If the learning rate is actually very low, you can look at this video. So, okay, this is a low learning rate, and as you can see, we are clearly getting stuck in this local minima over here. We are not even exploring the other side of this global minima. This is analogous to having very low ambitions. If we have very low ambitions, we always get stuck into this particular part of the loss function. We don't even know that on the other side there are even points which have lower minima. Whereas if we have very high ambitions, if the learning rate is very high, it might lead to oscillations like this. So it is very important to decide a learning rate which is kind of optimal, and sometimes that might be difficult to do, right? uh, so it turns out that there is another concept which is called momentum, and we'll come to this in the next lecture. It turns out that normal gradient descent is not too effective, and we always get either stuck in local minima or we keep bouncing here and there. That's why people introduce the concept of momentum in gradient descent. Here is how the momentum actually looks like. So let me start this video from scratch. Okay, so if you add momentum to gradient descent, here you can see that we are perfectly converging to the global minima, and then we kind of settle around here. What momentum does is that if we get stuck in local minima, it gives a small nudge, it gives a small momentum so that we are kicked out of that local minima. That's the whole idea of momentum in gradient descent. And as you can see, we have clearly reached the optimum value here. Great. In this code itself, actually, we can experiment with different learning rates, and we can see what actually happens. So let's try with a learning rate of zero point 0.5. So now I'm going to put a learning rate of zero point 0.5 over here, and I'm going to run this part of the code, and then I'm going to run this part of the code. Now let us look at the accuracy. As you can see, the learning rate is lower, so the iterations might take longer to reach the same level of loss which we earlier saw. But even earlier, at least we reached an accuracy of zero point 0.6 or zero point 0.7, but here we are getting stagnated to even zero point 0.5 or zero point 0.6. So this actually indicates that we have again got stuck in a local minima, and this is usually the problem with lower learning rates. Very similar to what I showed you over here, we are getting stuck in local minima probably. So if you run the animation for lower learning rates, so this is with zero point 0.5 learning rate, and if you start from scratch, you will see that the oscillations proceed something like this. Here also we try to get to the correct answer, but ultimately the optimum value which we get is a bit better, but not that great actually, because here also there are many misclassifications. For example, if you look at this particular section over here, this point the true value is red, but the background is blue, which means it's been classified as a blue point. So again, this is not very good. Here also you can see the accuracy has gotten stagnated to zero point 0.6. So this clearly indicates that just normal gradient descent is not working too much. But this gave us a lot of insight into understanding why learning rate matters, and why changing the learning rate can actually help us. Actually, increasing the learning rate can get us out of the local minima, but it can lead to many oscillations. Decreasing the learning rate too much can get us stuck in the local minima. I think that it's always better to start with a high learning rate and see what's happening rather than getting stuck in a local minima in a lower learning rate. And the reason for this is that if you have a high learning rate, so if you have a high learning rate like this, although it's difficult to converge, you'll at least see the different parts of the loss landscape. Like although we don't converge here, we get to this global minima multiple times in these oscillations. So we know that there is a part in the loss landscape which is actually very small. But if you start with uh learning rate which is very low, you might not even discover these other parts of the loss function. So I always actually recommend to start with higher learning rates, and then if needed go to lower learning rates. Okay, this actually brings us to the end of this lecture where we discussed about optimizers, gradient descent, and implementing them in Python. We tried to do a good job, and we definitely lowered the loss with normal gradient descent. and I showed you a glimpse of momentum, and I showed you how momentum can actually help us a lot, such as, for example, this video. This is an example of momentum, and here you can see that we clearly converge to the global minimum very nicely. So in the next lectures, we'll be looking at something called as decaying learning rate, and then we'll look at momentum, adagrad, ada delta, adam, etc., which are the modern ways to optimize or improve gradient descent a bit. So, with this, I would like to say that thank you so much, everyone, for sticking with me in this neural network from scratch series. We have done around 20 to 21 videos now, and I think this is the series on YouTube which goes in a lot of depth in neural networks. And I don't assume anything if you have seen the previous lectures. Thank you so much, everyone, and I look forward to seeing you in the next lecture.